Okay, so time for some more results about coequalizers and epimorphisms and equivalence relations and things like this. So firstly, let's again recall the definition of a coequalizer. So coequalizer of parallel arrows F and G from A to B is an arrow Q from B to capital Q, which is such that Q after F equals Q after G, and for any other arrow C from some B to D, such that C after F equals C after G, there exists a unique K such that K after Q equals C. Now, the thing is with a coequalizer, as we've been discussing, we can think of them in terms of, at least in the category of sets, and to be honest, basically in the categories of structured sets. We can think of capital Q here as being what we get if we take capital B and we form a graph on it, linking elements when there's something in A which generates one of the elements with F by doing F on it and generating the other one of the elements by doing G on it. So in other words, we link B and B dash when there exists an A such that F equals B and G equals B dash. Now we can think of Q as the set of weakly connected components of such a graph, and then we can think of the function little q as sending a vertex to its connected component. So anyway, what kind of example in the real world could we give to think about coequalizers? Well, I think there's quite a nice one, which is, say A and B are both a set of people, and then F sends a person to their father and G sends a person to their mother. And then capital Q here, you can think of this as all of the people organized into the maximum number of houses so that people with children together are in the same house. Okay. And then another sort of candidate, sort of something like C, such that C after F equals C after G. An example of that kind of thing would be if C was, let's say, the set of blood groups of your children. Okay, if you're a person. So it sends every person to a set of blood groups of their children. And that would have the property that C after F equals C after G. I think it would. Actually, I'm not sure, would it? Well, if you have a child, and then you take the father and the mother, yeah, you don't just want the set of blood groups of your children, you want the set of blood groups of all of the children in the house. Yeah, that's what you want C to be. Then it works out. Okay, fair enough. Right. So when we're trying to make this stuff match up, with Colin McClarty's chapter on toposes and how you can get at stuff like coequalizers and equivalence relations and things through the Mitchell-Benebow language. They've got a bit of a different take on coequalizers. So in particular, we've already discussed in some detail how this arrow k can be considered, but there's yet another guise to it, and that's formalized by this theorem 3 here. So theorem 3, let's get this lined up a bit better. Given an arrow c from b to d with c after f equals c after g, and again, we're going to suppose this is happening in sets because we just really want to get understanding of what's going on. And suppose that we have this arrow k from q to d. Well, then we're going to have this statement A holding, which says that for all elements little b in B, we have k of the connected component of B equals C of B. So this is our familiar condition star, and we're saying that this is going to hold if and only if for every W in capital Q and for every little d in capital D, we have k of W equals D implies there exists a B in capital B such that D equals C of B and W equals Q of D. So this is just like an alternative way of saying, because I mean, we've already shown that A, basically, there's a unique K that makes A work, and A is basically equivalent to the condition that K after Q equals C, the kind of commuting condition. But now we're saying here's another way to say it. And basically what we're saying here is that when we have that K is sending some W to some D, we can think of that as basically just meaning that there exists a B such that doing Q on that B gives us W and doing C on that B gives us D. So what's the proof? Well, firstly, let's go this way around. So we'll suppose A holds. And now suppose that K of W equals D. Now, since they have that Q is epic, so we can get that Q is epic by the kind of dual of the argument for why an equalizer is monic, which I've already gone through in a previous video. So we have that Q is epic. Well, since that's the case, that means there exists a B. Put that up there. Means there exists an element of B which is going to be such that W is equal to Q of B, which we could also write as the connected component of B. And so now A gives us this assumption A up here gives us that K of the connected component of B, which we could also write as K of W, is equal to CB. But we can also write K of W equals D by this assumption. So we have D equals CB. So we've shown now that W equals QB and D equals CB, and that's required. So we've now proved statement B here. Now we're going to go the other way around. We want to show that B implies A. So suppose B And now suppose we have some element B star of capital B. Well then, let's define D is equal to K of Q of B star. Okay, going around like that. That's obviously going to be an element of capital D. And we'll also let W equal Q of B star. So notice then that means that D is equal to K of W. So then we can use our statement B that we're assuming to say that means that there exists a element B, a little b, such that D is equal to C of B and W is equal to Q of B. And so by our lemma 1, which we've already discussed, we then have that, well, we can say that well, before we talk about lemma 1, let's just note that Q of B star, we can write that as a connected component of B star. And we're saying that's equal to W, but we're also saying that Q of B is equal to W, which is the connected component of B. So since the connected component of B star is equal to the connected component of B, lemma 1 gives us that C of B star equals C of B. Now, we have that K of B star is equal to K of W by this, okay, which is equal to D by this. And we know that D is equal to CB by this, and we know that CB equals CB star by lemma 1. So essentially we have that CB star is equal to K of connected component of B star, which is what we wanted to prove. Okay, so we've gone the other way around. We've now shown statement A holds from statement B. So that's it. That's the end of the proof. We've shown that A and B are equivalent. So basically, what we've shown is that this Q here is going to be this. When this Q here is this coequalizer, we have that this B here is an alternative kind of functional relation way to describe this arrow K such that K equals QC. So our next result is about equivalence relations and epics. So this is lemma 16.17 from Colin McCarthy's book. I'm not going through it in full topos proof. I'm just sort of mostly talking about what it means in set theory in this video. So given a relation R, which we might write as H comma K, which is a sub-object of B times B, there's an epic Q with H and K as the kernel pair for Q. This is the claim. So how do we see this? Well, let's consider this map here, which we could think of as the interpretation. Well, you can see how it's written, the interpretation of this quasi-set of W such that Y and W are in this R relation with each other, and that's interpreted over Y and B. Here, when I write stuff like R, Y, W, that's really shorthand if you've been really precise for something like that. Okay. But I mean, basically, we can think of this mapping I here from B to omega to the power of B in the category of sets, at least. We can think of it as sending an element B to the subset of elements of B which are in R relation to that element. So it sends a Y to the set, to the kind of equivalence class of Y, essentially. Now, here's the thing. We're going to have this condition holding that we're going to have the sort of equivalence class of Y is equal to the equivalence class of Y dash if and only if Y and Y dash are in R relation with each other. Anyway, suppose we have this epimonofactorization of this function capital I here. So we're going to break it into a epimorphism Q and then a monomorphism I. And then if you think about it, what's this monomorphism I? Well, it's basically going to be the image of capital I. So it's going to be the set of all kind of subsets of B which have something sent to them by this little Q here. In other words, it's going to be the collection of equivalence classes with respect to this relation R. Or if you want to think of it in terms of graphs, think of it as like the set of connected components of a graph. That's really what we can think of as, well, I mean, if we want to think of I as an inclusion monic, we can, or inclusion function, we can really think of Q as this sort of collection of equivalence classes. So now and then this little Q here, this is going to be sending an element B to its equivalence class. So then what we want to do is argue that this little Q here is going to have H comma K as its kernel pair. And here we're supposing that we can write this equivalence relation R as H comma K. So here's the thing then. Consider an element of B times B. It could actually be a generalized element, but whatever. And we'll call it X comma Y. Well, X comma Y is going to be in this equivalence relation. We can say that as X comma Y is in H comma K. And that's going to happen if and only if X and Y are in R relation with each other. But then by this kind of claim here, that's going to happen if and only if X and Y have the same equivalence class, which happens if and only if Q after X equals Q after Y. And saying that this happens if and only if this happens is basically saying that H comma K here is the kernel pair of Q. And that's it. That's the end of the proof.